Today we're going to examine parabolic behaviour. We're going to link to work that we've covered previously and also show how we can move forward and hopefully have a better way of actually graphing some of the equations that we've been working with. So the best way to get the most out of this particular activity is when you're asked to pause the video and actually have a go at the activity. Do that and then only unpause once you either get so stuck you don't know what to do next or you've completed the task. Then unpause the video and see how you went. I will go through the full working, so you might, if you want to fast forward that little bit to see if you got it right, then do that. Okay, so what we're going to do is we're going to examine an equation. So you can see here we've got y equals, as an example, y equals in brackets x minus 3 all squared subtract 4. And so what we're going to do, if you have a look at that, you can see there's a square there. So there's probably a link to parabolas, but that's what we're going to explore in more detail. So first thing, as you can see from there, what I'd like you to have a go at is to expand the brackets and collect like terms, and then what kind of equation do you end up with? So pause the video, have a go, and then unpause once you're finished. Okay, so you should have had a go. I've included every single possible step with this expansion, but what I hope you'll see is that you end up with a quadratic equation. Okay, so what we have up the top to start with, this is what we call the turning point form of a quadratic function. You'll see why shortly. So it's called the turning point form of a quadratic. Now we've looked at quadratics already and we've seen that a quadratic typically looks like 8 squared plus bx plus c, which is what you see down here. Okay, but we're going to be exploring a different way that a quadratic can be expressed and then how that might benefit us and what the positives of that sort of thing is. So we've taken from the turning point form, we've made it into a quadratic just to prove that it's possible. Okay, so let's review some of the key aspects of a parabola. So the next thing that I would like you to try and do, now you notice I've actually graphed it over here on the right, but I'd like you to try and solve each of those three tasks, as you can see there, algebraically. Now the stationary point, you just have to identify it, but we can also do it algebraically as well. So what I want you to do is find the x-intercepts of the equation algebraically. Okay, now I will actually do this one for you first, and then I will ask you to do the other two. So what is the axis of symmetry and what is the turning or stationary point? Okay, now we can identify all of those just from the graph, but let's do it algebraically. So let's identify the x-intercepts. So we can do it one of two ways. If we start with the function that we've just expanded, so if we go y equals x squared minus 6x plus 5, okay, we can then solve how do we find x-intercepts. X-intercepts occur when y equals 0. So we're going to let that function equal 0, x squared minus 6x plus 5. Now in order to do this, if you recall, we have to factorise. So we're going to factorise this now. We're looking for factors that multiply to give 5 and add to give negative 6. Well, those two factors are negative 3 and, so no, they're not. It's going to be negative 1 and negative 5, sorry. So x minus 1, x minus 5. So if I add those two numbers together, negative 1 plus negative 5 is negative 6. Negative 1 times negative 5 is positive 5. So we end up with our two factors, and then if you recall from a previous lesson, we use what we call the null factor law to find our x-intercepts. Okay, so that means that we've got x minus 1 equals 0 or x minus 5 equals 0. And so that gives me, I'm going to run out of room here, so I'm just going to come up here. That tells me that my x-intercepts are going to be equal to 1. So if x minus 1 equals 0, then x equals 1. If x minus 5 equals 0, x will equal 5. And we can see those 2 points very clearly on our graph. So that's one way we can do it. An alternative way is to actually use the turning point form that it came in originally. So I'm going to try that. I'll use a different color so you can see it. So I'm going to scroll all the way across so that we can have a bit more space. So y is equal to x, what was the function, just to make sure I don't make a mistake, x minus 3 minus 4. X minus 3 squared minus 4. Okay, so we want to find the x-intercepts. So just write that up here, find x-intercepts. Okay, so find the x-intercepts, we let y equal 0, nothing different So let 0 equals x minus 3 squared minus 4. Now, because this has been factorised, x minus 3 squared are two factors. So we can actually rearrange this. We can't rearrange the x squared minus 6x plus 5 and solve for x. It just doesn't work. You've got too many x's. It doesn't work. So we need to, but when it's in this form, we can rearrange it. So we're going to move, first thing we do is get rid of the 4. So we're going to move it to the other side. X minus 3 all squared. How do I get rid of the squared? I take the square root. Now, what you have to remember is if x squared equals a number, a, then x is plus or minus that number. So that's a key thing that you have to recall. Okay, what that means is if I take positive a and I square it, then I get a squared, I should say. I will make that, my apologies, I'll make that squared, so it's number. And if I have negative a and I square that, I still get positive a. Okay, for example, if x squared equals 4, then x can equal plus or minus 2. Because plus 2 squared is 4, negative 2 squared is also 4. So that's, when I move the squared down here now, I'm going to get plus or minus 2 equals x minus 3. Okay, the squared's gone, and now I move the 3 across, so I'll end up with 3 plus or minus 2 equals x. What does that mean? Well, it means that x is equal to 3 plus 2, or x is equal to 3 minus 2, which is 5, or x equals 1, which is what the answer we got earlier. Okay, so we can use one of either of those methods to find our x-intercepts. And so we've got that nicely on our graph there. What I would like you to do is, if you can identify, and I'll pause the video in a second, and I'd like you to try and identify what's the axis of symmetry and what's the stationary or turning point. Okay, so hopefully you've actually had a go at those now and you can see the solutions in front of you. So the axis, to remind you, the axis of symmetry is exactly bisecting the x-intercept. So, pardon me, exactly halfway between them. So if our x-intercepts are at 1 and 5, then halfway between 1 and 5 is 3. So our axis of symmetry is at the equation x equals 3. It's important that you write x equals 3 because it's an equation. The second part of it is what is the stationary or turning point. Well, the stationary or turning point is where the axis of symmetry meets the curve, which is at x equals 3. We need to find its y value. We can obviously clearly see it on the graph, but if we just did it algebraically, we start with our equation, y equals x minus 3 all squared, take away 4. I know that x equals 3, so I substitute 3 in for x. So I have 3 minus 3 all squared, so 3 minus 3 is 0, minus 4, which is equal to negative 4. So my turning point, stationary point, is at the point 3, negative 4. So what we've looked at there is an example of where we can use our turning point form to get some information. Now, I do want you to have a good look at the turning point and the equation. Do you notice that the 3 and the 4, ignore the signs for the moment, we'll deal with that later, but if you notice the 3 and the 4 are both in that form, hence the name turning point. So when you look at the turning point form, you get the turning point straight away, okay? It's also, I know it doesn't seem this way, but solving for x-intercepts is actually a lot simpler because you don't need to factorise. It's already factorised for you. So there are lots of advantages of working with a turning point form. So what we're going to have to learn how to do now, and that's what you'll be doing in the next activity, is going from the general form of a quadratic equation to the turning point of a quadratic equation. And that is something called completing the square. And that is your next task.